What do people think? Is this a reasonable idea? I'm getting a lot of head shaking. So this is, I have to confess, when I first heard this line of work about 10, 15 years ago, this sounded, absurd, like cute, but never going to be deployed. It looks less ridiculous over the years. And part of it is, if you think about it, users are more used to the idea of congestion pricing in the real world these days. There are many cities, notably London, for example, where congestion pricing for traffic is the norm. So if you drive through downtown London at rush hour, there are certain streets where you have to pay more to drive down those streets. If you drive down 880 these days, there is congestion pricing on the fast track lane. Right? The amount you pay to be on the fast track lane depends in real time on the traffic on that lane. So we as users are kind of getting used to congestion pricing. But the other reason it seems less ridiculous is that there is now an ecosystem of micropayments and digital currency, which makes this, again, more plausible. Right? Otherwise, this idea that you're going to pay in finer granularity for bandwidth on a per hourly basis would have seemed much, and still to some degree seems much less realistic. Anyway, so this is kind of the method of choice if you take an economic view of congestion. Not really deployed that much. The congestion pricing is not deployed at all, as far as I know, not yet on the internet. The main drawback with these is it requires a business model and a payment model that didn't exist on the internet back in the day, and even today it doesn't. A business model that backs this up doesn't quite exist other than in data center contexts. So the third approach, which is what we were working towards, is just this notion of dynamic adjustment. It's the idea that hosts are going to dynamically learn the current level of congestion in the network, and they're going to adjust their sending rate accordingly. Okay? That's implicitly what we were doing when we were all of us staring at that graph and saying how much A should send. There are many options for how to implement this basic idea. We'll get to them in a minute. In practice, what dynamic adjustment has won, it is how all congestion control solutions work. And it's one, I would say, and it's the reason we like it is the generality of this approach, right? It doesn't presume a business model. It doesn't assume that we know application requirements or user priorities or user preferences. It just carries the least baggage with it in some sense. What it does assume, though, is a notion of good citizenship. What do I mean by this is, in that example, we said, A is going to adjust its rate to 1 gig, and then A is going to adjust its rate to 1.5, and these two flows are sharing the link, and so each one is going to get 0.5. This is assuming that senders are going to do the right thing and cut their rate. Okay? So they're actually going to share. This is why, to economists, this solution makes no sense, because there is, sadly, very few real-world examples where users do the altruistic thing in sharing, right? Where you say, no, I'm going to take my salary and divide it equally across the companies. That's just not how the world works. And so while this seems absurd, this is actually how the internet works. And to this day, the internet is relying on the fact that we don't have too many malicious actors. When we get to advanced congestion control, we'll talk a little bit about why this state of the world has kind of survived and it does okay for the most part, and why it might change as well going forward. Okay, so with that, let's dig a little bit. The path we're going to go down is designing a dynamic adjustment scheme. Yeah? Yeah, so the question, it's a great question. The question is, why can routers enforce a correct share for, we're going to talk about this a little bit when we talk about fair queuing and router-assisted congestion control. It's actually a pretty hard problem, because for one router to know what is the correct share of a flow, it doesn't actually have all the information it needs to know that. Because, for example, let's say one flow is getting consuming very little bandwidth or at that router. It could be that the reason for that is that that flow is the sender is on some really bad connection and has very limited access bandwidth, and so it actually cannot consume more. But a router deep in the network doesn't know that. So what looks like unfairness to that router is actually not correct. It could give it far more bandwidth, but that source would not be able to exploit it. So it's really knowing exactly what the right share is each router doesn't have the full picture. The other reason is it's actually And this might be changing over time. It's computationally quite expensive for a router to do those calculations. And routers, if you remember what we talked about, they just do IP lookups, update checksum, send packets, and they have their hands full just doing that. So asking them to track how many flows, what is their share, what is the correct share is actually non-trivial for a router. But it's a great idea, thought, and we'll come back to it when we do more advanced topics. Any other questions? Okay, so let's dig into dynamic adjustment. What do I mean by that first? And I'm going to go through this fairly quickly because I hope we all have a pretty good picture at this point. So what I mean by that is, let's say we had that example where A was talking to E. So step one, the host A would have to somehow discover that it can send a 10 gig. When the route changes, A doesn't know that the route changed. But what it should be able to detect is that the rate it was sending at, which was 10 gig, is now congesting the network. And then it should be able to somehow discover that it should cut its rate to some lower rate of 1 gigabit per second. When another flow joins the network, what A should discover is now that even 1 gigabit per second is congesting the network. And then A finally should say that it somehow discover that ideally it should cut its rate to half a gigabit per second. Okay. So that's what we want to have happen. How we're going to make it happen, we haven't gotten into that yet. How do you think we could make it happen? Like, how could A know that information it needed at each of those steps? There's kind of two broad classes of solutions. Yep. Number of packets dropped, so it could observe, the host could observe the performance it's seeing. So I'm going to call that host-based congestion control, where the host is looking at the performance it's getting and adapting. That name gives away the other. The rate of acknowledgements, I would lump that into the same category. It's looking at what performance I'm getting. Right. And so the other class of solutions is what we call router-assisted congestion control, where the router is going to help the host figure out whether it's congested or not. And so those are the two kind of broad classes of solutions. The host-based congestion control, there's no special support from routers. They're completely oblivious, or they don't communicate any feedback back to the host. The hosts then adjust their rate based on what I'm calling implicit feedback from routers. And implicit in the sense that you do have a sense of whether your network is congested based on the ACKs you're getting back. Are you losing packets? What is the delay of your packets? Because remember, we're doing round-trip time estimations. If you see your round-trip time go up, that's a pretty good indicator that you're experiencing congestion. So this is kind of implicit feedback from the network or from the routers. Router-assisted congestion control is an approach in which the routers are going to explicitly signal congestion back to hosts. Right? And so it's an explicit signal in that you think of it as a packet is going through the network, a router is going to put something in the header that is then going to be returned back to the host. And that information in the header is going to tell the host something about congestion. What that signal could be can vary from something very coarse-grained, like a single bit that just says, I was congested, all the way to something much more advanced where the router tells the host, this is the rate you should send at. I'm actually going to calculate your fair share. Okay, so Van Jacobson's original TCP approach is a host-based solution. We are going to study a host-based approach in detail. We are going to just do a little bit of router-assisted congestion control. Okay, so just to give you a view of where we are in the design space, we've talked about, you could do reservations pricing, dynamic adjustment. Going down that path, we've gotten to host-based and router-based. And the path we're going to actually focus on is this particular one. Okay. Yeah? So the question is whether having the router send feedback actually adds to the network. So the way this is typically implemented is you don't send extra traffic or signals back to the host. You set a bit in the header. And so when the acknowledgement comes back to you, that information is reflected back to the sender. And we'll do a little bit of this when we do router-assisted congestion control. So let's just start to build out what that solution should look like. I hope you have a fairly clear idea in your head already about what this is going to do, but let's actually work it out. So each source is going to independently run the following, and the independently is important here. That's what makes it practical, and that's what makes it scalable. There's no coordination across hosts at all, and there's no coordination with the network either. So independently, what each source is going to do is it's going to try sending at some rate R into the network for some period of time. At the end of that period of time, it's going to ask, did I experience congestion during this last period? If it did, then it's going to reduce its rate in the next iteration. If it didn't, it's going to increase its rate in the next iteration. And it's going to repeat. Right? So this is a very basic dynamic adjustment. The one thing that's missing here is, what is the initial? You need to start at some initial rate R. How do you pick this? And so those are kind of the three components of our solution. How do we pick this initial rate? How do we detect congestion? And then how do we adjust to congestion? Right? What are these increase, decrease rules? So components of a solution, discovering that rate, detecting congestion, and reacting to congestion. Any questions on the components? Right. So detecting congestion, how do we detect? One we talked about was packet loss, that this was already in place in TCP. This is the approach commonly used by TCP. What is nice about loss as a signal? Yep. Is that it? Yeah, so in a way it's a fail-safe signal, right? When, in most cases, with one exception or a few exceptions that we'll get to, if you dropped a packet, that's a pretty unambiguous signal that there's a router along your path that's congested. There's not much ambiguity about it, so that's great. In addition, it had this side implementation or engineering benefit that was already something, the mechanisms for detecting loss were already in TCP, so why not exploit it? The cons, any thoughts? Why is loss not a good signal? Yeah.
Because it's like a direct cost to the host, so like they kind of discover that there's congestion at some cost because they have to send some traffic, which will get dropped.
Yeah, let me. So your argument that it came at some price to the host, I would agree with that. That price I would have said is delay, because you suffer delay before you suffer loss. And so you've already incurred delay in your sending. The other observation, which you have to have sent a certain number of packets and incurred some loss before you actually discovered what that congestion level was. True. Any others? Yeah? Yeah, actually, that's a good point. It's a very binary signal. You lost a packet. It's not telling you exactly at what rate you should send. Though the congestion control algorithm is going to learn that around loss, but yes. The other complication, which in a way we've not quite covered, is you could sometimes have loss for reasons other than congestion. One of them being checksum errors. Right? If your packet arrives at IP, you drop it because there was a checksum error. This is rare enough that people weren't concerned about this, that this is not a common cause for loss. Congestion is a much more common loss, with one exception, which is wireless links. So wireless links, you were sending packets and someone turned on a microwave too close to your tower, and there was interference on the signal, and the packet was corrupted, and you lost the packet. So this is actually quite common in wireless links, and so wireless links will not use, they do additional mechanisms to mask those errors. But so that's one reason why we don't like loss, is because sometimes loss is not a signal of congestion. It's a signal of, it happens due to interference or other reasons. The other complication, and this is very TCP specific, is that loss can get confused with reordering. So if you remember the way TCP reliability works, TCP uses cumulative acknowledgements. And so let's say that all your packets up to packet 5 had been received at the receiver. And so the receiver is sending acknowledgments saying, I'm expecting number 6. Right? And now you had sent packets number 6, 7, and 8, but the network reordered them. So they arrive at the receiver in the order 8, 7, 6. This is a very silly TCP thing, but TCP will, when it receives 8, will say, I'm waiting for 6. It's a duplicate ACK. When it receives 7, it will say, I'm waiting for 6. Another duplicate ACK. And if you remember what TCP reliability does, is it says, if I get a certain number of duplicate ACKs, that's a loss. I'm going to assume that that's a loss. Because at the TCP layer, not the network, TCP is assuming there's not that much reordering. And so sometimes if you have a lot of reordering in your network, the sender will get confused that there was packet loss and it'll slow its rate, even though the reason you were getting those duplicate ACKs was reordering. and not actually loss. This is one of those examples of where bad